Hello everyone and welcome to Advanced Functions Grade 12. In today's class, we're continuing to investigate the rates of change. In the previous class, we covered the average rate of change that defined by the slope of a second line that joins 2 points on the graph. But imagine if you were interested in instantaneous rate of change. For example, the car driver, he's always interested in his acceleration. How fast is he increasing his speed at the moment? Or for example, the following person would like to know how fast exactly this person is falling. If we have a function where height depending on time, for example. So what if you were asked to find instantaneous rate of change? What would you do? And that's what we are going to discover today. So to begin with, let's recall how we define the average rate of change. For example, let's say we had a specific graph. For now, it doesn't matter what shape or what shape or what properties does this graph has. And for example, let's say my graph looks something like this. This is not a function, this is a function. And let's say I pick 2 points on this graph, here and here. So my average rate of change would be defined as slope of a second line that joins these 2 points. And the slope would be right here. Basically, we are evaluating the tangent of this angle when defining the average rate of change. And let's recall the function that we use in order to evaluate the average rate of change. First point is f(x)(1). Second point is f(x)(2). And here is x1 and here is x2 respectively. And our function values are located here in y-axis. Or in other words, f(x) is here and x is here. So, and the function to define the average rate of change was as follows. Delta of f(x) was over delta of delta x equals, I will continue on this side, it will be f(x2) subtract f(x1) divided by x2 subtract x1. From the end, we subtract the beginning. So basically, difference in raise of a function over run of a function. This is run and this is raise. Raise in a range and run in the domain. But when we're talking about instantaneous rate of change, we would like to know what is the slope of a tangent line to this curve at a specific point. Let's pick this point, let's say in the middle right here. If we were interested in instantaneous rate of change, use some other color so I can emphasize it, purple. So in this point, we would like to find the instantaneous rate of change. And the tangent line to this curve at this point would be touching it only in this point that we are interested in. Okay, something like this. This would be our instantaneous rate of change for this function, for this specific moment of time and for this specific point. So as you can see, we no longer have 2 points. So how can we solve this problem? And this is where we this is where we're having a new term to this average rate of change function that will help us to define the instantaneous rate of change. So now let's imagine if we're treating this problem exactly the same way as we were treating the average rate of change, where we measured the difference in raise and run for 2 points. But let's imagine this time that this change in range and domain is incredibly small, like super small. Take a look at this example here. They break it up. They break second into fraction of a second, 2/10 of a second, 4/10 of a second. So we are breaking up our interval as small as possible. So in this case, let's say this change, this incredibly small change in x value, we would denote it as h. And h would be very small value traveling to 0. As the smaller the h is, the better. So now we can say that x1 equals x1 plus h equals x2. So these are x values now. We add some little change to x value. For example, if we were to measure something that changes with time, this h would be a very little time frame, incredibly small. So h2, so x2 would be located very close to x1, like this. But for this point, let's say my x1 is here in purple and x2 is here, and distance between them is h. So how do I define my function values now? If I had f of x2 and f of x1, I have to define those as well, considering the new input. So f of x2 would equal f of x1 plus h, and that's it. We would substitute x1 plus h for x2. So let's rewrite our average rate of change function, including new considerations about h value, which is basically step in x-axis, and which is going to be very small value. So my average rate of change function would transform into instantaneous rate of change function as follows. Let me use some area here. I'll move this up. So delta f of x or delta x would be equal to f of x1 plus h, subtract f of x1. Again, from the end we subtract the beginning, and here we would have x1 plus h subtract x1. After simplifying, you would see that only h is left behind on the bottom. And this is our function for instantaneous rate of change. And let's take a look at what we have in the textbook. Please take a moment to note down everything that I wrote on the screen, because it's very important. This example, this average rate of change, this instantaneous rate of change, definition of h as its incredibly small value traveling to 0, as well as how we transform f of x2 considering x1 plus h equals x2. Okay. So, guys, I hope I gave you enough time to copy this down, and let's proceed to this chapter. So, investigate the math. A small pebble was dropped into a 3-meter tall cylindrical tube filled with thick glycerine. A motion detector recorded the time and the total distance that the pebble fell after its release. The table below shows some of the measurement between 6 and 7 seconds after the initial drop. So here in the table, we can see that after 6 seconds of falling, the pebble passed distance of 208 centimeters, 0.39 hundredths of the centimeter. So, and we see the difference, the moment of time 6.2, 6.4, 6.6. You see they made a little step of 0.2 of a second. And how can you estimate the rate of change in the distance that the pebble fell at exactly time 6.4? Okay. And I would give you a hint in this case. Remember, the average rate of change would take 2 points on this graph, and we would have a second line joining these 2 points. And let's say if this was 6.6 and this was 6.2, it means that 6.4 was somewhere in the middle. And we would like to know the tangent line at this point, or the average instantaneous rate of change in this point. So think about that. How would you do that? And in this particular example, we're asked to calculate the average rate of change in the distance that the pebble fell during each of the following time intervals. So, as I said before, when we are trying to find the instantaneous rate of change, we have to take 2 points that are extremely close to each other. Okay, so in this particular case, we could take 6.4 and 6.6, or 6.2 and 6.4 time periods in order to estimate the average rate of instantaneous rate of change at point 6.4. As soon as those 2 points are the closest one we have, and so let's evaluate few average rate of changes and see how our estimate complies with them. So let's say first interval we're going to take 6.2 and 6.4, and second interval we're going to take 6.4 and 6.6. In this case, in the average rate of change would be as follows. FOX2, for example, 2 would be 6.4 seconds. 6.4 seconds subtract 6.2 seconds, and 6.4 value is 235.41, subtract 2 to 1.76. First case, let's use a calculator to help us. So it's going to be 235.41 subtract 221.76. It equals 13.65. So we would have 13.65 divided by 0.2. That's the difference. 6.4 subtract 6.2 would be 0.2. And we divide 13.65. We divide it by 0.2 and we get 68.25. 68.25. And what is this quantity? This is centimeters per second. So the speed of the falling pedal in the interval from in the interval of 0.2 of a second from 6.2 to 6.4. Let's evaluate the second one. It would be interval of 6.4 and 6.6. And 6.6 values 249.31 subtract 235.41, and again the step would be only 0.2 of a second, so we divide by 0.2, and we would have 249.31 subtract 235.41, 13.9 divided by 0.2, 69.5. So we have 13.9 divided by 0.2 and we get 69.5. And look, in this interval we have 68.25. In this area we have 69.5. Okay, and let's evaluate final interval from 6.2 to 6.6. So the second interval, or a second moment of time of 6.4 lays between those two values. So we would get 249.31 subtract 221.76 divided by 0.4 this time, because that's our interval. So 249.31 subtract 221.76, 27.5, and divide by 0.4. We're gonna have 27.55 divided by 0.4, and we get 68.875. Okay, 68.875. And 68.875, this is the average rate of change from moment in time on 6.2 seconds to 6.6 seconds. So it's somewhere, the truth lies somewhere in between. Remember, we have to make our step as small as possible, but in this case, it's only 0.2 of a second. Preferably, it should be even more, but we have what we have. Let's work with it. And here's two average rate of change from 6.2 to 6.4 seconds and from 6.4 to 6.6 seconds. And if I were to estimate the average rate of change at 6.4, I would say it lies somewhere between these two values. So how do I do that? I just find the medium of these two values. I would add them up and divide by 2. So 68.25 plus 69.5 divided by 2, 68.875. And you see that this would be my estimate average instantaneous rate of change, and it is same with the average rate of change from 6.2 to 6.6 seconds. So for where we took our interval where we're interested in the instantaneous rate of change between other two values, and we also could estimate it in that way. So great. Nice intuitive example. Please take a moment to copy down the solution. So I hope you had enough time to copy it down. And what is the instantaneous rate of change according to the textbook? The exact rate of change of a function y equals f of x at the specific value of the independent variable x equals a, estimated using average rates of change for small intervals of the independent variable very close to the value that we're looking at. So let's reflect on this investigation. Why do you think each of the intervals you used to calculate the average rate of change in part A included 6.4 as one of its endpoints? I think it was included there because that was the point of interest for us. Because if we would take some point that is far away from 6.4, we won't be able to estimate the instantaneous rate of change in this specific point. Why did it make sense to examine the average rate of change using time intervals on both sides of t equals 6.4? Which of these intervals provided the best estimate for the instantaneous rate of change at t equals 6.4? It made sense to estimate the average rate of change on both sides because we are examining the constant movement of an object. It's not, it couldn't be breaking into like, it couldn't be sliced. We would like to see how an object behaves in the motion. So, and in this particular case, 6.4 was here, 6.2 was here, 6.6 was here. And the instantaneous rate of change, it would be the same as we approach 6.4 from left side, as well as we approach it from the right side. It should be the same, or very close to each other. The way we came into this point for instantaneous rate of change, we're going to exit in the same way from this point. Even though 6.4 is not an endpoint of the interval used in the average rate of change calculation in part C, explain why this calculation gave a reasonable estimate for the instantaneous rate of change at t equals 6.4. So it actually gave us a reasonable estimate because as soon as this continuous graph, it won't have dramatic jumps, ups and downs when we move from one point to another. For example, in this particular case, we had a really small step for our function, which makes it almost continuous, endless for us when we are evaluating it. So taking two values to the left and right hand side from the second value also gives us a reasonable result. So let's move on. Apply the mass. Let's do several examples together to strengthen your understanding. The population of small town appears to be growing exponentially. Town planners think that the equation P of T, population over time, is as follows, where P of T is the number of people in the town and T is the number of years after 2000. Models the size of the population. Estimate the instantaneous rate of change in the population in 2015. So let's take a look at the definition of the preceding interval first. The interval of the independent variable of the form where h is a small positive value used to determine an average rate of change. So you can see here h, this is the small step that I was talking about at the very beginning. So we know that this graph is this function predicts the population after 2000, after year 2000. So that's, and we're estimating the population in year 2015. So where our variable t, the nearest value for year 15 would be 14 or 16 to the left or right. And let's take those values. You substitute them into average rate of change function. The step would be 1 year. And this is rough estimate because we took a step of a whole year here. It's very big number, but take a look that we have t as exponent here. So it's power of this function. So thus we cannot take fraction. I don't understand why they use a fraction. Maybe using calculator, of course, you can calculate the fraction power, but without it, it's gonna be impossible. So let's see the algorithm that they use. Calculate average rate of change using some dates that precede the year 2015, since 2015 is 15 years after 2000. Use t equals 15 to represent the year 2015. Use 14 T15 and 14.5 T15 as preceding intervals on the left side of 15 to calculate the average rates of change in the population. Okay, so here they evaluated the function with respect to t equals 15 and 14. They calculated that the growth of population was 3,464 people per year. Here they use the other preceding interval, where it's 4.5 years, basically. And there they see that it's even more people per year. Now, these were two examples where we used preceding interval, that is laying before the point that we're interested in. And now we're going to use following interval, where the second value we take is slightly bigger than the value we're interested in. So for this example, we use 16 and then 15.5. And you can see that we're getting closer and closer to the true value. Calculate average rates of change using some dates that follow the year 2015. Use 15 less than t or equal to t and t less or equal to 16 as following intervals, etc. So after evaluating it, as the size of the preceding interval decreases, the average rate of change increases. As the size of the following interval decreases, the average rate of change decreases. So we have to examine the average rate of change on both sides to find the trend. The instantaneous rate of change in the population is somewhere between the value above, and here where they add them up and find the rate median. So, and they came up with conclusion that 3,550 people per year, that's the increase in the population in year 2015. Solution B, selecting different interval strategy. Calculate some average rates of change using intervals that have the year 2015 as their midpoint. Centered interval, where t is 15, greater than 14 and less than 16. Again, we evaluate the average rate of change. And you can see that this value is pretty much close to the one we evaluated in previous example. But this is when we use the step of 1 year. What if we decrease our step and gonna make it half year? What would happen then? And you can see that your prediction would get even more accurate. It would get closer to the true value. Use 14 less or equal to t less or equal to 16 and 14.5 less or equal to t less or equal to 15.5 as centered intervals with 15 as their midpoint to calculate the average rates of change in the population. Examine the corresponding rates of change to find a trend. Using centered intervals allows you to move in gradually to the value that you are interested in. Sometimes this is called a squeeze technique. So to get a most accurate estimate, I would take the smallest step that possible. If you have data for when, for example, 1/1000th of a year pass, that would be the better step to use. So the instantaneous rate of change in the population is about 3,550 people per year. Centered interval, second technique. So let's sum up. First technique, preceding interval with following interval, and then finding the great medium between these two values, okay? And the second technique is centered interval, where we use our second value in between those 2 points, and we find the approximation by decreasing this range. And take a look at this, it's very interesting. If we take an average rate of change, for example, if this is the curve, this is our point, and this is the preceding interval, this is the following interval, and this is the centered interval. If we just take it like this, this is our centered interval. And this step, h, defines how accurate our estimate would be. So we have to make this h smaller and smaller in order to find the true value of the instantaneous rate of change. And you can imagine that as if this circle was shrinking and shrinking and shrinking all the way up to this single point where we have very little step. And that's where you get the most precise estimate of your instantaneous rate of change. Okay. By decreasing the step, you're making this area that we're working in smaller and smaller, which gives you more precise result. Okay, I suggest we move on. Let's take a moment to take a look at this example where we're squeezing centered interval, and you can see that the value is getting closer and closer to the true value. You see there, keep squeezing it more and more, which gives them more accurate estimate. You see up to 1/10,000, and that's not a limit. You can go even more. Please take a look at this example, and we'll move on. Let's not waste too much time on that. So I hope you had enough time to see this example. It's exactly the same way we used before, but we kept squeezing our centered interval as much as we could. And here is the solution B using algebraic approach and a general point. This is example I gave you at the very beginning, where we use H as our new term that we use here. So let's define the difference coefficient. If function P of population and Q are 2 points on the graph, oh, not function, the point P and Q, points on the graph of y equals f of x, then the instantaneous rate of change of y with respect to x and p can be estimated using the following formula. Value at the second point, subtract the value at the first point, and where h is a very small number, this expression is called the difference coefficient. Solution B, using algebraic approach and the general point. First of all, we write the difference coefficient for the average rate of change in volume as the side length changes between 5 and any value, 5 plus h. We can see that the function is x cubic. So this is x2, this is x1, 1 to 5, x to 5 to the third power. After simplifying it, we'll get the following expression. And here we're using 2 points, and let one point be 5.5 and 5 to the third power, or 5 to and 1 to 5, because you are investigating the rate of change for function volume, where x to the third power when x equals 5. And other point would be somewhere close, plus h difference. You see, this is on this graph, it's represented here, delta x equals h. And we can take h, a very small number, as 0.01 or negative 0.01, wherever we choose, but it should be as small as possible. And after substituting that value into function, we're going to calculate it. And as a result, we're going to get pretty much accurate estimate for the specific point. And I would prefer to use this method all the time because it's it's the smartest method. This is algebraic approach, so it can be implemented for any case. However, if you have functions that have, for example, empty point here or break, for example, then we cannot estimate the average rate of change where this break occurs. Okay, one more interesting fact. So here, an example where they select a strategy to estimate an instantaneous rate of change. Please take a moment to look at this example. Yes, I'm back. So in this particular example, nothing new. They have a table of values, and we have to estimate a rate of change at exactly 5 minutes. So this period of time here, you could use interval technique that we learned. For example, take an interval from 4 to 5, or from 5 to 6, or from 4 to 6. What they do here is they take a big interval and gradually decrease in it until they get to this point 5. They're using a shrinking interval, and you can see that the final estimate they get is 30 degree by Fahrenheit per minute. Fahrenheit. Now then they're using very small centered interval. The problem is they use the calculator to get a quadratic regression. They're determining the equation for this function where there's dependence of temperature with respect to time, and then they use this function substituting two values very close to each other. You see the very little step of 1/100th, and then they're using basically the algebraic way where we take h very small value. And finally, here's the list of key ideas from today's class, and let's review it. The instantaneous rate of change of the dependent variable is the rate at which the dependent variable changes at a specific value of the independent variable. X equals 8. That's quite obvious. And what you need to know, the instantaneous rate of change of the dependent variable in a table of values or an equation of the relationship can be estimated using the following methods. Using a series of preceding a minus h less or equals to x less or equals to a, and following intervals, calculate the average rate of change by keeping one endpoint of each interval fixed. This is x equals a. The location where the instantaneous rate of change occurs, basically. Move the other endpoint of the interval closer and closer to the fixed point from either side by making h smaller and smaller. Based on the trend for the average rate of change, make an estimate for the instantaneous rate of change at the specific value. Using a series of center intervals, calculate the average rate of change by picking endpoints for each interval on either side of x equals a, where the instantaneous rate of change occurs. Choose the endpoints so that the value where the instantaneous rate of change occurs is the midpoint of the interval. Continue to calculate the average rate of change by moving both endpoints closer and closer to where the instantaneous rate of change occurs. Based on the trend, make an estimate for the instantaneous rate of change. Using the difference coefficient and a general point, calculate the average rate of change using the location where the instantaneous rate of change occurs. So specific point and a general point where we have a little addition. Additional term, choose a value for h that are very small, such as 1/100th or 1/1000th. The smaller the value used for h, the better the estimate will be. The best estimate for the instantaneous rate of change occurs when the interval used to calculate the average rate of change is made as small as possible. that's it about today's topic. And we'll move on to practicing assignments, which are going to be part of your home assignment. And please take 5 to 10 minutes to review, for example, 4 and 5, and then I'll review them with you together. So I hope guys you had enough time, and let's move on to practicing exercise number 4. Here we ask to find the instantaneous rate of change for the given values of x for function x 6 times x squared, subtract 4. I would like to solve example B. So my value x is 0. I would choose the algebraic approach where I take really small h, incremental. So formula for my average rate of change would look as follows. Remember, we're going to have only h left below. And I'll take my h equals to 0.001. So now I have to evaluate my function value for x1 plus h. It would be, as soon as my x is 0, so f of x1 plus h would be equal to 6 times x plus 0.001 squared, subtract 4, and it's equal to 6 times 0.001 squared, and it would be 0.001. Subtract 4. Let's use my calculator to evaluate that. 6 times, basically it's no need. We would have 0.00006, subtract 4, and it would be equal to negative 3.00004. Let me see. 0.00006, subtract 4. I'm sorry, made a silly mistake. It would be 3.999964. Oh, here's also 9. And f of x1 would be simply negative 4. So now I substitute these values in here. I would have negative 3.999994. Subtract, but now I have negative 4 for f of x1, so I would add 4 and divide by 0.0001 and 0.001, 1,000. It would be so I have 0.00006 divided by 0.001. And as a result, I'm going to see that I have 0.006. This would be my instantaneous rate of change when x equals 0. So I hope this example is clear for everybody. Please take a moment to note it down. So I hope you got enough time. No? A little bit more? Oh, yes, sir. Hello. So, yes, sir. You came right on time for the problem solving part of our class. There is example I just solved for the instantaneous rate of change. So, would you mind do example 5? I'll do it together with you, and you'll do example 6. An object is sent through the air. Its height is modeled by the function h of x equals -5 times x squared plus 3x plus 65, where h of x is the height of the object in meters and x is the time in seconds. Estimate the instantaneous rate of change in the object height at 3 seconds. I would use algebraic approach where I take some small h value and my average rate of change function would take a following form. Now I just have to evaluate my function from one of the values. I would take h equals to 0.01, as small as possible. For this case, 0.001 would be enough. So, and we estimate the instantaneous rate of change of the object at height at 3 seconds. So my x1 would be 3 seconds. I substitute it into this function and would evaluate it. Now we have to just evaluate this average rate of change. Right away after opening the brackets, I can see that 65 would go away. 3 times 3 would go away. Only 3 times 0.001 would stay. And as well, -5.3. This won't go away. We have to open the brackets. You're gonna have -5 times 3.01 squared. I'll use my calculator in order to evaluate that. It would be 9.0601 plus 3 times 0.001 would be 0.03. Now plus, because we open the brackets, minus turns into plus. 5 times 9, 45 plus 45 divided by 0.01. Now I'm gonna have 5 times 9.0601. So here I get negative 45.3005 plus 0.03 plus 45. And the difference would be 0.2705 divided by 0.01. Now we have to evaluate it. It would be 27.05. This is my estimate, where it's meters per second. This is my estimated instantaneous rate of change for this function. Example 5. This example how to use techniques in order to find the instantaneous rate of change. Yes, sir, this is what the topic of today's class is. Do you have any questions about this particular example? So by the way, I have to remember, I have to emphasize, so as soon as you're here, that the attendance is taken in every class. The activities in the class are also considered in your final grade. So please be active. Take a moment to note down this solution. Yes, sir, can you hear me? Yes, sir, 1 2 1 2. So I hope you got enough time to note down that example. Let's solve one more example together and call it a day. The Canadian purchased a new car for 18,999. The yearly depreciation of the value of the car can be modeled by the equation where V of t is the value of the car and t is the number of years that Jacqueline owns the car. Estimate the instantaneous rate of change in the value of the car when the car is 5 years old. What does it mean? Okay. So again, we're going to use, let's use a shrinking interval this time to solve this problem. Well, 5 years, so we would take 4.99 and 5.01 as our two limits. Let me see. Just a second. So, okay. We're going to use a calculator in order to find the fraction exponent. And we're going to use a shrinking interval in order to solve this problem. I took two values very close to the second value. So we're going to find the average rate of change for these two values. In this case, not delta f of x, but delta of v of t over delta t, right? Change in value over time. So we're going to have v of 5.01 subtract v of 4.99 divided by difference in time. It would be 5.01 subtract 4.99. Now let's evaluate the function for these 2 points. I'm going to have 18,999 times 0.93 to the power 5.01 subtract 18,999 times 0.93 to the power 4.99 divided by 0.02. That's my difference. And let's use our calculator in order to find that fraction exponent. So 0.93 to the power 4.99 would be 0.6962. Let's round it up. We're gonna have 18,999 Let's bring it out from the brackets. Why not? This common factor for both of them. So we can bring it out of the brackets, and we're going to have 0.696. Yeah, let's go as precise as we can. 6193. This is what calculator gives me. Subtract 0.93 to the power of 5.01. And it's going to be 0.69513 divided by 0.02. So let me use the calculator to be exact in these calculations. We don't want to make a silly mistake. So 0.69613, subtract 0.69513. So we get this brackets equals to 0.00101. This is times 18,999 times is going to be 19.18999, and this is all divided by 0.02. And the result I'm gonna write it right here, that the instantaneous rate of change in the car price would be as follows: dollars per year. So $959 and some amount of cents. That's my instantaneous depreciation of the value of the car after 5 years. Now, specifically when the car is 5 years old. But take a look at it. My instantaneous rate of change is positive, isn't it? So it means that this car would become more expensive in 5 years. If my rate of change would be negative, that would mean that the price for the car went down. But in this case, I can see that the price for the car went up. So this conclusion from this particular example. Thank you for attending today's class. I hope you learned something new today. Please review your Google Classroom regularly for new assignments. This assignment would be posted there as well. Thank you for your time and have a great day.